All right, so screen share here. Let's go over this. Good. And here we are. We got week 4 going on, and yep, let's just begin from there. So at this point, we are finishing up section number 3 material, section 1, section 2 done, ba-boom. On to section number 4. There is, if we log into our CSUN Canvas page, a little section or a little in the instructions for section 4, a little notice to try to open up Raven and make sure that it opens up. So I just want to take a look at that really quick, just to make sure we're all on the same page with that, because we will start using Raven next week. And it is imperative that it opens on your computer, and we have that downloaded and everything. So let me log in to our Canvas page. Just take a look at that really quick, show you what's going on. Then I'll open up Raven to show you what it should be looking like. But ultimately, we come on down to section 4, instruction. And it says, hey, keep studying the terminology, good. File frequencies of musical notes, good, we'll be referencing that. But if we come down here, open Raven in the Raven toolbar. So open up Raven and then go into the Raven toolbar and you go to File, open sound file, and the menu should pop up that says examples. And there's a whole bunch of different example sounds that you can open up. I want you to open up one in particular, which is the Raven sound file. And if for some reason you can't find it, you can also download it from our course page or Canvas page. I'll show you where that is as well. But ultimately, want to make sure that you can open up a sound file and you can play it, and that's it. So you'll ultimately open it, play it. It should have a configure new sound window when you first open it, and I'll show you that as well. But we want the window preset to always be physics of music default. In the past, there had been some issues with when you download it, that was missing sometimes, but that has been rectified. So it shouldn't be any funny business with this not showing up. But ultimately, want to make sure that you can open up a sound file, opens up on your computer, that you have Raven, number 1, and going from there. There is a question in the quiz pertaining to how many ka sounds the Raven makes in the sound file. But let me just go ahead and jump over to opening up a Raven so you can see some things that I'm talking about. So I'm going to go back home here and then minimize this stuff out of here. That close. And I got Raven Pro 1.6 right here. I'll go ahead and double click it to start to open it. And it might take a second to open, but it will eventually do so. There it is, open it up. Cornell Lab, great. I don't need any new software right now, so let me just get rid of that. And this is what the Raven screen generally looks like when you open it up. Again, configuration wise, depending Mac, PC, it might have a slightly different view to it, but it's pretty cohesive between Mac and PC. That is, there's not a bunch of differences like there are in Audacity. Nonetheless, you're asked to go into File and then open Sound File. And if we do that, see what pops up here. Right now, I have this location open on my computer, but by default, it goes to examples. So let me go ahead and find where the examples are. And here they are right here. So you should find that when you go into open sound file, that it goes straight into Raven examples. And one of them in here is in fact the Raven AIF sound file. So you would click on that, then open it. I'm not going to open the Raven one because I want you to open that one. I'll open a different one though. Let's just open up the, what sounds good today? Let's go with the Lark Sparrow. Let's see what that sounds like. So I'm going to double click that. And once I do, it brings up this. Now, it's really important that when we open up sound files in Raven, that we always change this to physics of music default. These have parameterized settings that are specifically tailored for the sounds that we'll be looking at so we get good results in terms of the data that we want. So you should definitely find that there. Just change that to physics of music default, press OK, and kabam, it opens up the sound file. It's 3 different screens here. We'll get into that much later, but this top one here is the waveform, which is a recording or a record in a sense of the pressure variations that occur with respect to time. You see these little ink marks here. Well, each one of these little ink marks is a portion of the sound that this bird, the lark sparrow, is making. So like right in this region right here, if I said, hey, how many little sounds, individual sounds does a lark sparrow make? I could count them out. 1, 2, 3, 4, 5, 6, 7, 8. There's 9 individual little chirps that he makes right there. And we could play this. So I note that I have not shared the sound. So let me share the sound as well so that you can actually hear it when I play it. So I have this little region highlighted, so that's what's going to play. And then there's the play control button right here. I can play it. So you ready for this? Listen to this. 3, 2, 1. Wow, that's 9 really quick sounds. Here we go. If you wanted to play the whole thing, you could click over here and play it. Pretty cool, pretty cool. But for now, that's what I just want to make sure that you are able to open up a sound file and change it into physics music default setting and go from there. If for some reason you don't open it in the beginning with physics of music default setting, you can go into view and window preset and change it there as well. If you open up with default power 1.3, you'll see something that looks a lot different. Actually, you'll just be missing one of the graphs, but you can always go back in here and change it as well. So that's just kind of good to know. Now, I will say if you do not find examples in there for whatever reason, that we do have, save that, we do have the sound file in our Canvas page. So if we go back to Canvas here, I can scroll down and now I got to open this up so you have it visible because it's not published right now. But these are sound files that we're going to be utilizing in the course. I'll expand this out now and you'll see that, oh yeah, there's a violin, a trumpet, a French horn, female voice, and there's a raven right here. I'm not going to open this sound once again because I want you to do it, but the way that you would go ahead and open the sound in Raven is you have to download it to your computer first. So for instance, I wanted the female voice sound on my computer. I'd go ahead and click on this. And then I would, oh, wow. But I download it here, press some download, and then it downloads to my download file. And then I could go back into Raven and say, hey, file, open a file, and then I could change this and go to my downloads, which, oops, that's not where I want to go. Downloads right there. Downloads and dun, 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 dun. Seems I'm not seeing it in here. It should be the last one that I just downloaded. So maybe I did something a little bit off there. Downloads, or it's referencing a different folder, name Mark Sparrow.
No, it was there. I
Was
just
it?
saw it. Like maybe if you go right a little, yeah, it's right
Oh,
here.
there it is. Yeah, you're right. So they put it in alphabetical order. Oh my gosh. Thank you for that. I appreciate it.
Of course.
Then we can go ahead and double click on that, set to physics of music default setting. I can open that up. This one has 2 channels. So sometimes some of the recordings will have 2 channels. We don't need to look at 2 channels. There's no difference for the right and the left speakers with the sounds that we're looking at. So I'll just change it, uncheck one of the channels. And then we have this. This is the recording of the pressure variations that are occurring with time. And if I wanted to play it in Raven, I could just put a little marker where I want it to start and press play. And there we go. So either way, you either open up from the examples file that's in Raven itself, or if you can't find that, just download it from our course materials page or our Canvas page and open it up that way. But again, main thing, open it up, make sure that it opens good and that you have physics music default setting, and that's it. That's it. We're not using Raven yet. So from there, let us go ahead and resume what we're looking at here and look at the topics for today. Topics for today, we're going to look at pitch versus frequency, octaves, harmonics, and overtones, Fourier theorem, and then the synthesis of complex tones that will be correlated directly with the experiment that we are going to do for this particular section. So first off, pitch versus frequency. We got that every musical note has a specific frequency that we define it by. And yeah, it's human made, the definition pertaining to the frequencies, but that's how we go ahead and understand the specific frequencies of the musical notes for A, B, C, D, E, F, G, and the sharp or flat keys as well. So what I want to do right now is note that, hey, C4, the fourth octave of C, has a frequency of 261.62 hertz. We could do some calculations with it traveling through air. We'd have the wave speed would be 1,128 feet per second. And we could then calculate what the wavelength of the note C4 is as it travels through air. One cycle of C4 would contain or be contained within a distance of 4.31 feet as it travels through air. That's just a little example just with C4. What I want to do is also go back to our Canvas page and come on down to our course resources and now open up this particular file here, which is the frequencies of musical notes. And what we want to be able to see is, once again, each musical note itself has its own specific frequency that it's defined by, and what's known as the equally tempered scale, which is the modern scale that's used currently. So we've got these different columns here. You'll see musical note, first octave, then second octave, third octave. We'll get into the definition of octaves here momentarily. But if you just start looking, let's just look at the fourth octave. We have C4, 261.62 hertz. C4 sharp or D4 flat, 277.18. D4, 293.66. And so on and so on and so on. Each of these notes is defined by a specific frequency, A4 being the easiest, 440 hertz. But this is what we've got. The composition of the musical scales has the frequency correspondence, and again, it's very well defined. Going back to a little PowerPoint here, what we want to do is look at octaves. So octaves are really iterations of the same note, just at either a higher or lower pitch. So you can have a very low C or you can have a very high C, for instance. C4 is the middle C, but you can have that same particular note played on the piano at a higher pitch or a lower pitch. The way that octaves work is that if you double a frequency, you step up one octave. You have a higher pitch. You go from, say, C4 to C5 if you double the frequency of C4. If you half a frequency, you step down an octave. You have the same note, but it's a lower pitch iteration of it. So a little for instance here, just kind of writing out here, the first octave of A, which we call A1, the little subscript tells us the octave, that has a frequency of 55 hertz. If we want to step up to A2, the second octave of A, a little higher pitch iteration of A, hey, we just double A1 and we have 110 hertz. We want to go to the third octave of A3, we double the frequency of A2. If we wanted to go to the fourth octave, we would have Yeah, 440 hertz, then 880 hertz, and so on and so on. So if we go back and look specifically at the frequencies of those musical notes, you can see that in here. And it's again easiest to see in A because we have nice whole numbers here. First octave of A, 55 hertz, second octave A, 110, then 220, then 440, then 880, then 1760, then 3520. But that's the same thing that we get with all of them. Double 32.7, you get 65.4. Double 65.4, you get, there's some rounding issues here, but you get 261.6 or 61.8 really. But again, there's a little bit of rounding things that doesn't give us clean numbers for everything, but double that to get to C5, hey, double it and you get 523 approximately, and so on and so on. That works for everything. So what we can do just to understand the concept, not just of doubling the frequencies and such, but of actually hearing octaves, is we can open up Audacity. Why not? So I'm going to open up Audacity. I'm going to add a new mono track in here. I'm going to go ahead and generate a tone. We want it to be a sinusoidal wave, sure. And I'm going to make it 220 hertz, which will be the note A3, third octave of A, 4 seconds long. Sure, it has a certain amplitude. Let's just go ahead and generate it. So here's we know that it's just going to be a sine wave if we zoom into it, but this is 220 hertz, A3. Let's play it. Ready? 3, 2, 1. All right. There's A, sure. So what do we want to do with this? Well, what happens if we go ahead and we change its frequency to 440 hertz? Oh, but it looks like things got packed in more. It's still just going to be a sine wave if we zoom in, but now let's play this. Wow. So it sounds kind of like the same note, but it's just a higher pitch regarding it, higher pitch iteration. If I wanted to go step down, oh wait, let's go step up again. Why not? Go mono track. Oops. Then I'll just put in a new track then. We'll generate a tone. Let's make it an 880. 880. So now I have two. I'm going to go ahead and mute the 440 and just play the 880. Here's 880 hertz. Hopefully that didn't get anybody's ears too bad, but that was 880. If we go back to 440, the same note, just a different pitch iteration of it. And likewise, we could go and say, let's just take a 220 and a half and go from A3 to A1. Oops. To have ourselves be at 110. Go to 110 now and play this. That you probably have to turn up your speakers for because it's pretty low pitched, but I'll play it again. Hopefully you get the idea there that the notes are the same notes. They're just different iterative pitches of that same note. And again, with octaves, you're just doubling a frequency or having a frequency to either step up an octave or step down an octave. That's great. So at that, get the concept of octaves, fantastic. And then here's just a little example, half of a keyboard or half of a piano keyboard, where we've got the layout of C, D, E, F, G, A, B, C, D, E, F, G, A, B, C, D, E, F, G, A, B, C, D, E, F, G, and it just keeps on going like that, generally up to 8 octaves on a full scale piano. But then we've got the black keys, which are the sharp keys, or you could call them flat keys as well, but those all have their specific frequencies, and those repeat themselves as well. C sharp, D sharp, F sharp, G sharp, A sharp, C sharp, D sharp, F sharp, G sharp, A sharp. But as we go to the right, we're going into higher and higher octaves. Great, great. So now let's take a look at some aspects regarding what are known as harmonics and overtones. Now, we talked about harmonics a little bit at this point and said that if we have a periodic complex tone, it has to be composed of harmonic frequencies, where harmonic frequencies are integer multiples of some root frequencies, the base frequency in a sense. And by base, I mean that which the others are built upon. So let's just look at something here. Harmonics and overtones. So in general, overtones, they're just natural vibratory frequencies of a given system. They are the natural frequencies that the system wants to vibrate at. Overtones, great. They're just the frequencies of the system. In many systems, the overtones, when we have multiple overtones being occurring, the higher order overtones are not integer multiples of some root frequency. And when that is the case, we will have something that does not have a well-defined pitch because it's not going to be periodic. If we have a sound that has multiple frequencies that aren't all integer multiples of the root frequency, you get something that's non-periodic. And again, if it's not periodic, it doesn't have a well-defined pitch. We can't say it has a fundamental frequency, and it is the fundamental frequency that defines the pitch of the sound itself. But then we come over to harmonics. Harmonics, a harmonic is still just a component frequency, but it is a special one. It is always an integer multiple of what we'll call the fundamental frequency, or we'll call that the first harmonic. The combination of this fundamental frequency with these higher order frequencies will produce a sound overall that is still periodic. And it will be periodic just as in the same way that the fundamental frequency is. And that's why the fundamental frequency is going to ultimately define the pitch of the tone. Because as we add in harmonics, we don't change the overall frequency of the sound. What we do is change the quality of the sound. We change the color, the sound quality, or that's known as the timbre. So it's the fundamental frequency itself that defines the pitch of a sound. The higher order harmonics within the sound, they add to the uniqueness of the sound itself. And that's what we're going to be looking at a bit today as we go on into the section for experiment, kind of getting the aspect of that. But it's an important distinction in this course. Vast majority of sounds that we're going to be looking at are sounds that are composed of harmonic frequencies because they're going to be well behaved, they're periodic, we can identify a singular cycle, we can calculate fundamental frequencies, wavelengths, we can look up fundamental frequencies and determine what sort of closest musical note that is, all that good stuff. For sounds that are composed of non-harmonic overtones, the analysis gets quite a bit more complex because you don't have something that's periodic anymore, and they're not as kind to analyze. Thus, we will mostly stick with the notion of harmonic sounds. And besides drums and percussive instruments in general, we have most of the Western instruments produce harmonic tones, as do the vowel sounds when sung or spoken. But that's about it. Anyways, we'll be looking at that as time goes on. But right now, again, you want to get that idea. So, question quite some time ago was whether a stretch string, like a guitar string or piano string, really could vibrate at different frequencies simultaneously. Like, can it really have different frequencies occurring simultaneously? And the answer is yes. Yes, it definitely can. But it really wasn't until Jean-Baptiste Fourier came along and was able to mathematically show how that composition occurs. It was understood that there is some overall fundamental frequency that controls the pitch of the sound, and that the higher order frequencies add to the uniqueness of the sound, but it wasn't really something that people were able to demonstrate in terms of sound itself. Again, until some mathematician, Jean-Baptiste Fourier, came along and was able to successfully show that that was indeed possible. So I just need to move a couple little things out of the way. And what we want to look at is this loaded string app here to get the idea of multiple frequencies occurring simultaneously. So let me open that up. And this is a nice little applet that you use from time to time just for demonstrative purposes. And what we have here is what we'll envision as being a string that's fixed at both ends. And it's undergoing some sort of vibration. This vibration here, where the whole thing's going up and down, would be indicative of the fundamental frequency. This would be the lowest frequency that's possible for this particular system. Again, a string fixed at both ends. So we call this the first harmonic, fundamental frequency. And we could count it out, right? We could count out cycles. 1 cycle, 2 cycles, 3, 4, 5, 6. And it seems like, hey, there's 1 cycle occurring per second. So in terms of just a wave, this would be a 1 hertz sine wave, or a 1 hertz wave, we'll just say. But I can stop this. Where's the stop button? Clear. And I can say, well, we also have what is known as the second harmonic, which would be a frequency that's twice, 2 times that of the fundamental frequency. So we name the harmonics, the number of the harmonic, by how many times it is frequency-wise relative to the fundamental frequency. So let me activate the second harmonic. This would be the second harmonic, the oscillation or the vibration that correlates with it. Now I've got 2 sections vibrating up and down. And if we wanted to count out cycles here, we're going to note that they're occurring twice as fast as they were for the previous wave itself. So let me count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. What's going on there? They're occurring twice as fast. What would this be? This would be a 2 hertz wave. Fantastic. A third harmonic will occur 3 times as fast as the first harmonic. Now we got 3 sections oscillating up and down. And if we count these out, we got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, counting about in threes because every 3 is going to be 1 second. And we can keep on going with this and get the idea of the 4th harmonic, 5th harmonic. They start being hard to start to count out. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I can't see that quick, so I'm not sure if that was right or not, but nonetheless, the idea is as we look at higher order harmonics, their frequencies are increased by integer multiplicities of the fundamental frequency. So now what we want to see is how can 2 different frequencies or 5 different frequencies or 20 different frequencies be occurring simultaneously? What does that look like? And well, let me just activate the first harmonic. And on top of that, add in the second harmonic. And now we see something that is still doing the same thing over and over, but it doesn't look like this single oscillation just up and down. We've got this sort of side to side motion that goes with it. And with that, we can still count out complete cycles. And every time that it gets up, that peak gets up to where my cursor is, I'm going to count that as 1. So 1, 2, 3, 4, 5, 6. Seems like there's 1 full cycle occurring every second, right? Well, there is, because the fundamental frequency is 1 hertz. If I want to see the 1 hertz oscillation in here, that's the yellow now. It's embedded in there. That the overall period of the more complex oscillation is still equal to the period of the fundamental frequencies oscillation. If I want to see the imprint of the second harmonic in here, well, it's in here. It's just superimposed on top of the fundamental frequency itself. So we have really those 2 individual sine waves, those 2 individual frequencies occurring simultaneously, adding on to one another. If I wanted to put in another one, sure. Things get more complex, but I added in. And what do we get? things changing. This is a lot more complex oscillation here. And now that involves three different harmonics, first, second, and third. But the first harmonic is still dictating the overall rate at which that complex oscillation is occurring. They're the same. It's still a 1 hertz complex oscillation, just as the fundamental frequency is 1 hertz as well. So no matter how many we added in here and how complex we ended up making it look, we would always have that this is just going to be a 1 hertz wave. That's it. A 1 hertz overall wave. It has all these different frequencies in it. Those add to the uniqueness of the wave itself, but overall, fundamentally, it's still just a 1 hertz wave. Complex though. So that's the idea with multiple oscillations occurring simultaneously. And again, it was a man known as Jean-Baptiste Fourier, who was a French mathematician, that was able to ultimately produce a theory and a mathematical representation of how this can occur. So we'll look at that briefly. We don't want to get too tied up in mathematics here, or likely you do not care to do so, which is fine. It's fine, but let's go ahead. Come on back here. Look at this guy. Is that what he really looked like? Yeah, something like that. I don't know. I wasn't around then, so I'm not quite sure, but this is the picture that comes up of Jean-Baptiste Fourier. And there we go. He looks pleasant. So this is the actual Fourier theorem for the Fourier series for building periodic waves out of sine and cosine waves. You don't have to worry about this whatsoever. If you've seen it before, or if you have the mathematical background, maybe you appreciate it a little bit, but this is just adding up sine waves with particular frequencies. And ultimately, its theory says that you can make any function f of x periodic over any interval by adding up an infinite number of sine and cosine waves, which is kind of a mouthful, right? Like, wow, you want to add up an infinite number of them? That's crazy. But we can start to get approximations, and this is how synthesizers ultimately work. So if I start zooming in, oops, try to zoom in right there. We looked at this before, but looking at this specifically here, we've got three different sine waves here, three different sine waves. But what we should notice is that each of these sine waves has a frequency that is an integer multiple of this larger sine wave, this blue one. So we can see that this blue one, we have 2 full cycles of it, right? Then we can come over the red one and say, well, how many full cycles of the red one fit within 1 full cycle of the blue one? 1 full cycle of the blue one starts here, goes up, goes down, and then ends right here. And notice that both the red and green one have ending points right there, and they start over. And that shows explicitly that some number of the red waves or some number of the green waves fit exactly within 1 full cycle of the red wave. Excuse me, 1 full cycle of the blue wave. Oof. So if we count out the number of cycles for the red wave, we got 1 cycle, then 2 cycles, 3 cycles. 3 full cycles of the red wave fit exactly within 1 full cycle of the blue wave. Thus, if we say that the blue wave is the fundamental frequency, we'd have that the red wave is the third harmonic, because its frequency is 3 times that of that fundamental frequency. So right now we could say we've got a fundamental frequency, we've got a third harmonic, and then we could look at the green wave and count out how many cycles it has in 1 cycle of the blue wave. We've got 1 cycle, 2 cycles, 3 cycles, 4 cycles, and 5 cycles fit exactly within 1 full cycle of the blue wave. Thus, we would call this the 5th harmonic. So we add those 3 different frequencies together, let's say. And when we do so, this is what we get. We're just adding point by point vertically. If it's above, it's positive. If it's below, it subtracts off. And we just add every point. We superimpose these waves on each other. And this is what we end up getting when we add those 3 sine waves together with those particular frequencies. We get something that looks completely different, right? It still has this sort of sine wave shape to it, but it's got embedded on it other sinusoidal types of behaviors. but this is how those three sine waves add together. Something that we should note is that the period or the time that it takes one full cycle for the blue wave to occur is the same amount of time that it takes one full cycle of this complex wave to occur. They're both ending the same point in time. And that's because we're adding harmonics together. So the idea is that we can produce particular wave shapes, particular wave forms. And in this particular scenario here, what trying to produce or producing an approximation of is a square wave. The more harmonics we add together with, again, particular frequencies and amplitudes, the closer we can get to something that is a square wave. So this would be the first 12 non-zero harmonics being added together, where I've already went through and calculated what particular amplitudes they have to have in order to produce a square wave. And hey, we add them together, and as we add more and more, we get that this top gets flatter and the junction or the transition from high pressure to low pressure gets sharper and sharper. And as we add an infinite number together, we get truly a square wave, like the one that we're looking at in the last experiment. But that's the idea of this synthesizers. We can synthesize particular wave shapes that have correlated specific sounds with them. And again, that's how synthesizers ultimately work. So what we want to do for our experiment this week is synthesize a couple waves. We're going to synthesize an approximation of a square wave using Audacity, and we're going to synthesize an approximation of, this is a violin sound, trumpet sound, with utilizing specific frequencies, which are all going to be harmonic frequencies, and specific amplitudes. And well, we're only using 6 different frequencies here, but we'll still get a decent approximation of a square wave utilizing this. But that's one part, building a square wave. And then the second part is building synthesis of another complex tone. This one's going to be an approximation of a trumpet. And it shows you right here what yours should end up looking like. This is 2 full cycles of the complex waveform that you are going to be building utilizing Audacity. So let's go take a look at Audacity and how you go about building things in there with multiple sine waves themselves. So jumping up, let's not jump. Let me look back at the frequencies here. We got 0.9, 0.3, 0.18. So we'll start off with that. I'm going to open up Audacity. I'm going to close these down. And what you're going to do is produce different tracks. So I'm going to make one track. And in that track, I'm going to make a sine wave that's 100 hertz. And I am going to have it have a particular amplitude of 0.9, as was stated in the actual instructions. So I'll go generate tone. We want sine wave. We want it to be 100 hertz here, 100 hertz, and the amplitude to be 0.9. And we can do 4 seconds of it. That's fine. But there we go. I got a 100 hertz sine wave right here. You want to play it? We could play it. It's going to sound really soft. You might have to turn up your speakers, but it's just going to be 100 hertz, which is pretty close to G2 sharp, but 100 hertz nonetheless. Now, what we want to do is actually put in another track. So now we'll stick in another track. And in this track, I'm going to generate another tone, but this one I'm going to have be 300 hertz. 300 hertz with an amplitude of 0.3, as was stated in the instructions. So I'm going to put this one in. Now, what you want to do now is add these 2 tracks together to produce one new sound that is composed of both a 100 hertz and 300 hertz. So let's do that. How do we do that? First off, we have to select both sounds. So if we go to select and all, that's the easiest way to make sure both or all the sounds are selected. And then we can go to track. And what we want to do is there it is, mix. We got to mix, and we're going to mix and render to a new track so that we're going to add these two together and produce a new track of the addition of both of them. So you mix and render to a new track. Now, what I want to do now is zoom in and kind of see what we've got here. So I can go ahead and use the zoom tool some way, shape, or form. Click, 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 zoom in. And what do we have here? We got a 100 hertz sine wave up top. We got a 300 hertz sine wave here. And then we have those two waves added together here. And if we notice some things, that one full cycle of this 100 hertz wave is the same as one full cycle of the complex wave that we've made. And that 3 full cycles of this 300 hertz wave fits exactly within one full cycle of the 100 hertz wave. Again, this is the third harmonic. The period of the complex wave for a harmonic ends up being the same as that of the fundamental frequency. So they share how many cycles there are per second. That's it. But that's not all. What do we want to do? Hey, let's go back and play. Zoom out. Oops. Zooming in. Zoom tool. You come over here. Zoom back out. And zoom issues here. There we go. So zoomed out. And what I want to do is, again, play the 100 hertz by itself. Play the whole thing. Sorry. Select here so it knows where to start, and then play the 100 hertz only. Kind of foghorn sounding. And then I'm going to play the complex tone, which is 100 hertz and 300 hertz. And we want to distinctly recognize some things here. So ready, 1, 2, 3. First thing to recognize is it's the same note. It's still 100 hertz. It still has the same pitch, but it has a different quality to the sound, right? It was stronger sounding, number one, and it had a little bit of more buzz to it on the back end, but it's still the same 100 hertz wave. I shouldn't say same, excuse me. It's still a 100 hertz wave. It just has a different quality to it. Why? Because it's a 100 hertz and 300 hertz wave added together. Fantastic. Well, let's add another track. Oops, add a track, mono track. And this one, let me go back and reference. We want 500 hertz with an amplitude of 0.18. So I'll add another track. Let's generate it. Tone 500 hertz now, which would be the fifth harmonic because it has a frequency of 5 times the fundamental frequency, given the amplitude of 1.8. Boom, add it in there. Great. Now we've got these 3 different waves in here. And now we want to go ahead and select all 3 of them. And again, mix them together. Tracks, mix and render to a new track. And now you can zoom into this one. Now this is going to be a 100, 300, and 500 hertz sine wave added together. And what does it look like? It looks a little bit different. Looks a little bit different, but it still has a overall period that is the same as the fundamental frequency. There's still one full cycle of the complex wave that's contained within one full cycle of the first harmonic, 3 cycles of the 300 hertz, 5 cycles of 500 hertz. But again, let's go ahead and play this one now. Back out. Not have something highlighted. Here. And now this is going to sound a little bit different than the one before. It's going to have more, I don't want to say character. It's not going to sound so soft though. This comes out a little bit louder. I'm going to turn down my speakers. The more harmonics we add in, the louder it's going to get. So beware. 3, 2, 1. Again, comparing that to just the 100 hertz sine wave. Same pitch, different quality. So what you're going to do in this experiment is go through adding in individual sine waves and listening to the sound and listening to how it changes, but also how it stays the same. Pitch stays the same, quality changes until you have all 6 sine waves. And then comes the point where you're going to take some screenshots and things like that. So let's jump over to Canvas just to open up the guide for it. And coming on down, section 4 guide. So outlines it here, putting in 100 hertz, sticking it in there, putting in another track with 300 hertz, zooming in to see things. That's great. Mixing them together, mix and render to a new track. Fantastic. And then from there, it has you continuing to do this, adding more and more, but it also asks you to start to make some measurements of things. So this is an important aspect because we have to change some of our settings. Instead of having numbers of samples now in Audacity, we want to have seconds. So it says here, adjust zoom levels needed. So you have 4 and 6 wave cycles of the complex wave, and then also have length and center of selection active, which you should have, but you are going to change, let's say, let's show it here. You're going to change the measurement itself to hours, minutes, seconds, milliseconds. So just showing that again on Audacity. For the PC, it's over here. It has the length and center of selection. Good. I can click on this and I can change it to hours, minutes, seconds, milliseconds. So now it gives me time measurements. For Mac, the controls over here, and you have to click on the little gearbox. No, excuse me. You just have to click on the little chevron next to the top one, which is the length, and make sure you change it there. The little gearbox allows you to change it from one setting to length and center of selection, which hopefully you've been able to find at this point. But the reason we're going to do that is because what can we do? Again, we can come zoom in to this complex wave. And once we have the zoom levels enough, I can highlight a full cycle. And when I highlight a full cycle, it tells me then in seconds what the period is. Because if I have one full cycle highlighted and I measure the amount of time contained in that, that is the period. Well, this is 0.010 seconds. The amount of time highlighted here, which is 1/100th of a second. What happens if you take the inverse of 1/100th? You get 100. 100 what? Well, 100 hertz. And that would be the overall period or overall frequency of this complex wave, which is the same once again as the fundamental frequency. So as you kind of go through that once again, but the important thing is that you're able to change the unitization for the measurement tools from samples to, really, we want the milliseconds part there, but it's all tied together: hours, minutes, seconds, milliseconds. And note again that the little dot there, it's not a comma. This one is a decimal place. So it's hours are those two, minutes are those two, seconds are these two, and then these 3 here are milliseconds, which you'd read, this would be 10 milliseconds, for instance, or 0.01 seconds. So you're going to go through that. Eventually, well, that has you highlight over 4 full cycles. That's fine. Getting the amount of time in 4 cycles, and then you're taking a screenshot. Take a screenshot of the whole Audacity to play with the 100 hertz, 300 hertz sine wave and the synthesized waveform zoomed in with 4 full wave cycles highlighted and the length of time being displayed. Bam, save and label it. So I don't have the whole thing shown, but you should have definitely the 100 hertz, the 300 hertz, and this one shown highlighted and go from there. Then you're going to delete this complex wave, just exit out, and then add in the 500 hertz. And then you're going to add in the 700 hertz, 900 hertz, and 1100 hertz. And eventually you're going to have all of the individual waves along with the synthesized wave, the complex one with all of those added together. And then you can take a screenshot of that, zoomed in enough so you can see 4 full cycles highlighted of the complex wave. And that's it for the synthesis of the square wave or approximation thereof. It does say proceed to save the sound file on your computer. You do not need to do this. If you want to try to save it, that's fine. But if you do it incorrectly, build it incorrectly, it's not going to help you out. Used to have people using this for the next experiment, opening it up in something else, but I'll just say you don't need to do this part. If you do it, it's okay. No big deal. If you don't, that's fine too. But you can kind of read through this about it remaining periodic. That's great. And then part 2. Whew. What are you going to do? You're going to do the same thing, basically, except you're going to be synthesizing a different tone. The different tone will be an approximation of a trumpet, and it has different frequencies. We're going to have an first harmonic or fundamental frequency of 349 hertz. And then all of these are integer multiples of 349. These are the amplitudes that you have to put in correctly. If you do not put in the amplitudes correctly, it won't add up to be what we want it to be, and it will not look correct. But this one, you do not need to go one by one and then listen to it and render it. Just get all 10, put them all together, synthesize it, mix and render, and then zoom in so you can take a screenshot of the musical tone. Don't forget to have descriptions of each thing that you're looking at. One thing for this musical tone, we know what the fundamental frequency is, right? We're told 349 hertz right here. This is the first harmonic. First harmonic and fundamental frequency are synonymous. They mean the same thing. So we'll bounce back and forth between utilizing the first harmonic and the fundamental frequency for naming the aspect there. But if we know the fundamental frequency, the period of the wave is then 1 divided by that, because period's 1 divided by fundamental frequency. So if you do 1 divided by that, you get a time of 0.002865 seconds. That then is the time contained in 1 full cycle of that particular wave. So what you are to do is zoom in to a particular aspect somewhere between, so you have 4 and 8 full cycles, and then say how much time is contained within that portion that you're zoomed into. And what does it depend on? Depends on how many full cycles you actually have shown. Each full cycle will have a time of 0.002865 seconds. So if you have, say, 5 full cycles shown that you're zoomed into, then hey, 5 times this is the amount of time that you have shown. It's that easy. But you have to be able to, number 1, count out full cycles, and number 2, understand the relation between the fundamental frequency and the period of the sound itself, and how we can use that to understand timing aspects itself. So after that, you got 1 screenshot there. Definitely note in the description the number of cycles that you have present and the approximate number of full cycles displayed. Your description should include the amount of time shown. Yeah, sorry, I said that kind of weird. The amount of time that's shown within the zoomed in portion that you have for the complex wave, and approximately the number of full cycles displayed, and that'll be it. You'll make a single PDF. You've only got 3 screenshots for this. Make sure that they all have good descriptions, and that's it. Make sure that you're understanding the key aspects here, kind of a reiteration of them to some degree, but that's pretty much that. Go back to our home here. You'll note that there is both the experiment results upload, which is those 3 screenshots and descriptions. Then there is also an experiment test for this one as well, just like there was for, or is for, this one here. Why are those dates? Oh no, I was looking at those dates wrong. So that is pretty much that for this week. What did we focus on? Ideas of notes being defined by particular frequencies, the idea of octaves being 2 times or 1/2 a given frequency, stepping up or stepping down the same note, just a higher or lower pitch, and then the composition of complex tones relying on harmonic frequencies, where harmonic frequencies are always integer multiples of the fundamental frequency, and the harmonic number tells us how many times it is regarding the fundamental frequency. So begin like this being 700 hertz, and this being the fundamental frequency of 100 hertz, we would call this the 7th harmonic. This would be the 11th harmonic, and so on. Also note that for the square wave, this was for the square wave here, that we're only using odd integer multiples of the fundamental frequency. There is no 200 hertz, 300 hertz, 200 hertz, 400 hertz, 600 hertz. That's just how square waves end up being composed, that they don't have even integer multiples of the fundamental frequency. And that's just mathematically how that comes out. And it happens in some other natural sounds as well, where there's only odd harmonics, but for the square wave being a very synthetic wave, it's how it needs to be built in order to have its own properties. That's it. Whew. All right, so at that, see how I get back. So share, stop and share. So at this point, it is any questions pertaining to what we just did. I know a couple people have some questions about how their screens are looking for the last experiment and stuff. But first, we'll just start with questions with any of this material. All right. So then we'll go ahead and say, if you don't have any questions and you want to vacate, perfectly fine. Be well. It's been a pleasure. If you have questions and you'd want to stick around, free to stick around, and I will do what I can do.
Thank you, Professor.
Yes, of course. Myra, I know we've been talking back and forth. Let's get this resolved, right?
Yeah, that's right. Can you hear and see me?
Yes, yes, I can.
Okay.
So if you want to screen share, you can. So you're still having the same problem where you're not seeing the tools.
Yeah, I'm not seeing any of the tools. That's my main problem.
I thought that you had sent me a screenshot that actually had that they're there, but then I couldn't go back and find it. I was like, where did that go?
Yeah, I don't know. I feel like every time I open it, something different pops up. So it's
Because
like
you're on Mac, right?
Yeah, it's
Mac.
really confusing for me. But let me show you what pops up when I do open it
Yeah.
right now.
So I know Mac has its own toolbar that controls everything. And if you have the screen overlapping with that main toolbar, then you're not going to be able to see what that toolbar has. I think that that's what's happening.
Okay, I'll just share my screen and I'll show you like which way I do it.
Yeah,
And you can tell me if I'm doing it wrong or right.
sounds good.
Um, video. How do I share the screen actually?
Down at the bottom, or it depends where your controls are for Zoom, but there should be one that has like a green box and an arrow that
Oh
says
yeah, I see it
share.
now. Oh, it says that I can't share the screen because you're sharing yours.
I'm sharing mine still. Oh, I am. Okay, good. Sorry about that.
No, you're fine. Okay, let me go ahead and try it out. Can you see it?
Yeah,
Okay. So I just go to Odyssey down here and I open it and
yes,
this
yes,
is
yes. So don't do anything yet.
okay.
So up at the very top toolbar, those
Uh-huh.
are all your controls right there.
Like all of these
Yeah,
or
yeah. You got
okay.
tracks, generate.
Oh, okay.
So I think
So
initially you had this maximized or moved over, so it was covering those up.
mhm.
And then you
So I
can,
know for like one of the experiments I had to go to tracks, correct?
yes,
And
tracks, add
then
new mono track.
oh, okay.
Go ahead, click it,
Okay.
and then go generate,
Generate.
go down to tone,
mm,
and then put in 100 hertz or put in whatever you want.
Okay. Can I just do this?
Yeah, just put generate then. And then you can click on the plus magnifying glass over to the left more. It's almost directly underneath. No, not that one. Sorry. Left.
You're fine.
Then
Magnifying glass.
down. Right.
Oh,
Yeah.
yeah, I
Almost.
see it now.
Yeah, that one. And then
Yeah, I'm blind myself too, so I'm like I'm squinting.
so click on that a few times. I'm not sure if it does it from there. Keep clicking. Let's see. It's shifting the time, so that's good. And if you keep on clicking on that, it'll eventually zoom into the wave enough where you can see the individual cycles.
Oh yeah.
There you
Okay.
go.
Okay. Okay, so that's how you do it. Oh my gosh. That was so easy. I feel like I'm so sorry. I feel like I
No, don't
wasted
be
your
sorry.
time.
Don't be sorry. Not at all. Not at all.
Okay. Then
Because
I'll
like
go ahead and work on the experiments tonight and just get them done so I can turn them in.
okay, that sounds good.
Yeah.
So just make sure that if you click off of your Audacity screen, then the tools go away, I think.
Okay, yeah, I see that
Usually
now. I
click-
see that
yeah,
it's happening. It went away, yeah.
yeah. So click back on Audacity screen. Oh, no, it's
Oh
okay.
wait.
No,
All right, are you sure?
yeah.
Okay.
And I think the other two people that were sticking around were having the same problem, so
Oh, okay.
that's why they left. one of
Okay,
them
I'm
is-
glad I can demonstrate then.
Cool.
All right
good?
then. Yeah, I think those are all my questions for right now.
All right, sounds good.
All right then. Thank you so much, Professor. Have
Yeah,
a great
of course.
evening.
Yeah, you too, Myra. Take care.
Bye-bye.
Bye-bye.